In this module, we try to propose a method to calculate exponentiation value using divide and conquer procedure. The problem is calculating x to the power of y for some integer values of x and y. Immediately we get an idea of having a for loop as shown in the slide and going on multiplying x for y times. This seems okay and also looks immediately that the complexity is proportional to y, order of y. Of course, complexity in terms of number of multiplications, it is y. However, if you consider the multiplications complex into account, then we have to worry about the how much time is required for carrying out one multiplication also. If we consider both x and y are n-bit numbers, and already we understood in the previous modules that the crude approach to multiply two n-bit numbers is proportional to n square, that is the order of n square. Thus, the total complexity will be function of y and n square. However, what is the worst possible value of y? That is, y is also n-bit number. Thus, the largest possible value of y is 2 power n. Thus, the complexity of this algorithm can be said as 2 power n into n square. If we assume that n, the number of bits, 512, then the complexity becomes 512 whole square into 2 to the power of 512, which is ridiculously very high. Let us visualize the same problem in terms of base 10 system. We know in base 10 everything is powers of 10. We know every 10 will be power of 2 cube. Thus, the worst case complexity will be in terms of base 10 if we represent. 512 means approximately 2 power, is a 2 power 9, 512 whole square into 2 to the power of 512. That is nothing but 2 to the power of 530. But the same thing, the same thing can be considered as 2 power 530 is considered as 10 to the power of 159. So that is the order of complexity if we represent in the base 10 system. And even if we assume that a 1 gigahertz machine which takes 10 to the power 9 cycles per second, which gives 10 to the power 9 cycles per second, and if we assume that one operation can be done in 1 second, so we require in total 10 to the power of 150 seconds to complete worst case time. So the same thing, if you convert it into hours, as shown in the slide, it becomes 10 to the power of 142 years. So that is the worst case complexity of raising one number by another number. This is ridiculously very inefficient. We require some efficient procedures. In the following slides, we will consider divide and conquer technique. In this divide and conquer method, we use the following concept. If we wanted x to the power of y, the same thing can be represented as x to the power of y by 2 whole to the power of 2 if y is even. Otherwise, the same thing can be represented as x into x to the power of y by 2 whole to the power of 2. And also, x to the power of y is equal to 1 when y is equal to 0. So, we can build up a recursive function basing on this truth. However, we have to worry about the runtime complexity of this solution. This algorithm of exponentiation calculation may require log y recursive calls. The following recursive function will calculate x to the power of y. We have included trace for this recursive function call for y value of 7. Thus, the order of complexity becomes log y into n square. However, the y value, worst possible value of y is 2 power n. So, thus log of y, that becomes n. Thus, the order of this algorithm becomes n square into n. That is, n square is meant for calculating product of two n-bit numbers, and n, so worst case that many recursive calls are required. Thus, the complexity of this algorithm becomes order of n cube. This is comparatively smaller than the previous solution. Can we improve this divide and conquer procedure further? Yes, we can improve by trying to eliminate recursion. We propose the following algorithm. So, we consider the y value, rather I say bits values in the y. For example, if it is 45, binary code of 45 is 101101. So, we will consider the bit values from left to right. If it is 0, just simply square it. If it is 1, square and then multiply with x. This we proceed by considering the bit values of the y. Thus, we start with 1, then 1 into 1 and then multiply with x. Thus, we get x. Then next bit value is 0. That's x into x square. We'll calculate x square. Then next bit value is 1. So we square that one. That is x to the power of 4 we will calculate. And then we will multiply with x. Thus we get x power 5. The next bit is 1. So x power 5 square it. So x power 10 into x. Thus x power 11 will get. Then next bit is 0. So simply we get x to the power of 22. Then next bit, last bit, the rightmost bit, the least significant bit value is 1. Thus we square x to the power 22 into 2. That is x to the power of 44 into x. That is x power 45. So if we propose to do that one, what you call calculate the exponent, then we will be eliminating the recursive calls also. Thus the algorithm will be efficient. Here in these slides, we have proposed a divide and conquer procedure.